Hello everyone, we're starting off with a little number trick here, and then we'll use this to kind of introduce today's topic as we talk more about the concept of proofs in geometry. So we're going to play a little number trick here, and we'll just start off with step one and work our way down. We're going to do this twice, so create a divider between the first and second attempt. We'll just use the two columns. So here, let's pick a number between 11 and 98. So let's pick 15. Okay, you could pick whatever number you want and do it differently, but I'll start with 15. Let's double that number. All right. So thinking about that, that means 2 times the number. So 2 times 15 gives us 30 by this point. Let's add 4 to the number. That brings us up to 34. Let's multiply that answer by 5. A little help from my calculator here. Give me 170. And then let's add 12 to the answer. So we're up to 182. And multiply your answer by 10. So 1820. Subtract 320 from your answer. So subtracting 320 gives us 1500. Cross out the zeros in your answer, and we get 15. And you notice we ended up with the same number we started with. Alright, now we wanted to explore why this works. We want to understand how it happened. So we're going to go through this a second time, but instead of picking a number, we're going to pick a variable. We'll use x. X represents the number we could pick. It could be any of those numbers, and we're going to look to see what happens to x as we go through this sequence of steps. And this will help us to understand a little bit about why this number trick works. Okay, so first we're going to double the number, so that means we're going to multiply it by 2. So 2 times x is what we currently have. We've doubled our original number. Now we're going to add 4 to the number, so 2x plus 4. This is the expression. You don't have to put it in parentheses, but that's the expression that represents the value of our number up to this point. Now we're going to take that number and multiply it by 5. So that does help to wrap this expression in parentheses because it's 5 times the entire value of that number. And let's use our distributive property to multiply that out. So 5 times the 2x gives us 10x, and 5 times the 4 gives us 20. So this is the value of our number up to this point. Next, on step 5, we're going to add 12 to that answer. Well, for adding 12, we want to add it and combine like terms. So that means we have 10x still, and when we add 12 to the 20, we end up with 32. Alright, so we're going to multiply that answer by 10. Now what that means is we have to multiply the entire value of that number by 10. So again, it might help to wrap it in parentheses. And if we use our distributive property, then we have 10 times 10x gives us 100x. And then 10 times 32 is 320. All right, right on the edge of the paper there, but this is the value of our number. Notice what we have up to this point is we've just been adding numbers in, we've been multiplying, we've been making them bigger and bigger. Until we get to this point, we have 100 times our original value that we picked plus 320. To make the number trick work, we're trying to figure out how do we get back to the original number we started from. So now we have to take out all the numbers we've been adding in up to this point. And so you can see, well, if I wanted to get x by itself, let's get rid of the 320. And that's what that step says. Subtract 320 from your answer. So the 320 is taken out. At this point, what we want to do is we want to divide away the 100. And that's what this is saying by cross out the zeros. Same thing as dividing by 100. So to make a number trick work, you pick any number, you add and multiply, make it bigger and bigger and bigger, until you finally get to a point where you just decide, okay, I'm done adding and multiplying. Now let's figure out how to return back to the original, and we take a look at what we have, and we're then going to essentially eliminate all of the value that we've been adding into it. Now, what does this have to do with a proof? Again, with a geometric proof that we're going to be doing, we can only do one step at a time. So you notice that each of these steps that took you through the trick was exactly one operation at a time. We did not combine steps. We did not double and add 4 all at once. No, we broke it down one operation at a time. And that's key, because in a proof, we have to have one idea at a time. We can't smush them together and try to make two different ideas work in a single line. Also, sort of that cause and effect. If I pick a number and I double it, well, then the effect is my number is 2 times bigger. If I take that number and add 4, well, now the effect is that my number is 4 times bigger than what came before. So again, we see that cause and effect happen with these number tricks as well as our proofs. All right, so that's a little bit of an introduction to why we're going to be doing proofs with this idea of one idea at a time. So this draw conclusions, that's what we were doing right over here on the side with using the variable of x. Now when we're working with proofs, we're going to need a lot of ideas to be able to then connect those ideas to create a logical statement. So we need a lot of properties, we need a lot of definitions, we will be using postulates and even other theorems to connect these ideas together to create new theorems and new ideas. So we're starting off with the basics, and these are properties. These are properties of algebra, which means it's possible that in your Algebra 1 class you spent like a day or two looking at these, and you probably moved on and you probably haven't seen them since. So they should look familiar, even if you don't remember all of the details. I do want you to recognize that these properties are what we're going to be using today in terms of describing or explaining what operation we're performing on our proofs. So, the addition property of equality. If it says property of equality, that means we're going to be doing this operation to both sides of the equation. So pretend this is an equation. A doesn't have to be just a number. It could be an expression. It could be a whole bunch of terms. But the point is we have something on the left side and something on the right side of the equation. And whatever that equation is, we can simply add a value to both sides. So we're using A, B, and C as placeholders. So if I have something on the left and something on the right, I can add, as long as I add the exact same thing to both sides. Now again, C might be a number, but it doesn't have to be a number. It could be an expression like 2x or 5y. We could be adding 5y to both sides. We could be adding 2x to both sides. The point is it has to be the same thing and to both sides. Subtraction property of equality means that if we have an equation, then we can subtract from both sides as long as it's the exact same value. Multiplication property of equality means that we can then multiply both sides. A times C on the left and B times C on the right. The division property of equality means you take your equation and we can divide both sides by the exact same thing. Again, you're not allowed to divide by 0, so that's why this C cannot be 0 is included. The substitution property of equality, this is a little bit harder to explain with this particular setup. So let me add a little bit more. I'm going to add some detail. Let's say for a moment we have if A equals B and B equals C. Let's say that's the setup. We need a little bit more information. If I'm going to do a substitution, we're not doing the same thing to both sides. It's not the same operation, but rather we're taking something out and putting something else in its place. So there's a couple ways we could set this up, but let's say we're working with this, and I'm saying, hey, if A equals B, and the idea of B is also equal to something else, we can take that C and drop it in B's place. So it would look like A equals C. What we've done is we've done a substitution. We've taken B out, and we've put in its place what B is equal to, which is the C. That's an example of substitution. You'll notice this distributive property is not a property of equality, which is why I put it outside the box here, because all of these are properties of equality. technically it's just a property. It's not a property of equality because there's no equal sign, there's no equation. You can multiply that A to each term inside the parentheses, and you get A times B plus A times C. Alright, so those are some key properties. Turn the page over and we'll take a look at a couple of descriptions with our vocabulary of what we mean by proof, and then we're going to use algebra to start explaining what a proof is and what it looks like and how it's structured. This is really the only day we're spending with algebra proofs. It's really meant to be just an introduction to the format and the thinking of how we set these up. As we go on, we'll be doing geometric proofs, but we're using algebra today to just help us sort of bridge the gap between the algebra we know how to solve and the proofs that we're trying to make in the future. So, how do we describe a proof? A proof is a logical argument that shows a statement is true. A proof is a logical argument that shows a statement is true. So, logical, again, each of our statements have to be true in order for the entire proof to be true. We can't use false or silly ideas. And this idea of argument, we're not talking about you and I are angry at each other and shouting at each other. It's not that kind of an argument. An argument here is more of like you are taking a position and you are defending it. You are backing it up. You are supporting it with evidence. And the evidence is all the ideas that come in the proof. And the goal is to make sure a statement is true. We're going to set up our proofs in a two-column format. All right, so a two-column proof has numbered statements A two-column proof has numbered statements and corresponding reasons. That show an argument in a logical order. So we are going to have numbered statements and corresponding reasons. That means we're going to number the statements. We're also going to number the reasons. So there's two columns. Each column will have numbers to indicate each new idea that we are using. Now when we do a proof, there has to be a logical order. You can't just throw ideas down in any order you want. No, they have to chain together to make a cause and effect, cause and effect, cause and effect pattern, and that's what builds the proof and shows it as true. So that's why we mean logical. So let's start off with our example number one. We're going to solve this and we're going to write a reason for each step. So, first of all, the emphasis here is not really the algebra. We're assuming you can do this. Though if you're a little bit rusty, this is a good review. But we're simply using this as a way to demonstrate what you need to do when you set up a proof. So we're going to have a column for statements. We're going to have a column for reasons. We usually separate the titles of the columns with what we're going to be writing down. And then we're going to number these off, and however numbers we need will be however many steps it takes to solve this. Again, you can only do one operation at a time in a proof. You can't combine steps. You can't combine two different operations at the same time. We always start by writing the given information on line 1, 2x plus 3 equals 9 minus x. And there's no operation that we've done yet. We haven't really started doing any math, so this is just given. So reason number 1 is always given because that's the problem given to us. Now we're going to perform a variety of operations or use properties to figure out how to solve for x. So, where might we start? We could try to move the constant terms to the same side, or we could try to move the variable terms to the same side. Got to pick one or the other. You can't do both at the same time. So I'm going to start off with the x's. I'm going to move all of the x's to the left. Now, line number 2 is going to be the result of that operation. So if you want to show work, you have to squeeze it right here between line 1 and line 2. We're adding x to both sides of the equation. And so the result of that is 3x plus 3 equals 9. Alright, so you could sort of do that in your head, but if you want to show the work, you have to squeeze that work between line 1 and 2, because line 2 is the result of that operation. Now, what operation did we do? We added the same value to both sides. So this is the addition property of equality. So there's a few ways to abbreviate this. Some will just go APE, addition property of equality. Some will use plus sign for addition and PE for addition property of equality, or addition POE for addition property of equality. So there's several ways to abbreviate it, but I'm going to write it out here so we can continue to practice recognizing what that name is. Addition property of equality. Okay, x is not isolated yet, so we have another step to do. Let's move the 3 to the right hand side, so our constant terms are on the right hand side, so my work is to subtract 3 from both sides of the equation, and the result of that goes on line 3. So we have 3x equals 6. What did we do? We did subtraction. So this is my subtraction property of equality. Alright, well, x is not by itself yet, so we need more steps. So x currently is being multiplied by 3, so to undo that, we're going to divide both sides by 3. And so now x is by itself. The answer is 2. And the operation we did was division, so this is my division property of equality. Alright, so that's an example of a 2-column proof. Notice, you have to number the statements and you have to number the reasons. Don't leave those numbers out. Because if you leave those numbers out and your handwriting goes uphill or downhill, then it's harder to figure out which reason is paired up with which statement. In the homework today, you're going to be having problems like this. And again, I hope that the algebra is not a problem, not too much of a problem. The emphasis here is not so much on the solving of that, but pairing up every work of every step of work with a reason. So let's see another example here. In fact, a few more examples here with example 2 and 3, and then we'll look at a few more properties. So example 2, here is our column for statements, column for reasons. Statement number 1 is the problem itself, so 3 times the quantity x minus 5 minus 2x equals 21 plus 10x, and reason number 1, that's given. Alright, so the first thing that I'm going to do is I'm going to distribute that 3. So here we have 3x minus 15 minus 2x equals 21 plus 10x. Remember, only one operation per line, so you can't combine and do more work than what we've just done here. This is our distributive property. This is the only property that is not a property of equality. It's just distributive property. Line 3. Let's see, what should we do? Before we start moving terms back and forth from one side of the equation to the other, recognize that we have like terms on the same side. These can be combined. 3x minus 2x is just 1x. There's the minus 15, there's the equal sign. The right-hand side stays the same. So notice we did not use a property of equality because we didn't do an operation to both sides of the equation. We only focused on one side, And we could do that because these were like terms, and we can combine like terms. So our reason is combine like terms. Another possible way to explain that reason is to use simplify. There we are. Okay. Alright, taking a look at our choices now. I am going to combine the terms with x. I've got an x on the left and an x on the right, so now I'll be using a property of equality as I am subtracting 1x from both sides. So we have a negative 15 on the left. On the right we have a 21 plus 9x, because 10x minus 1x is 9x. But the operation we did was subtraction, so this is my subtraction POE. Alright, so there's the abbreviation, property of equality. Line 5, let's move the constant terms to the left-hand side. So here we have a 21. I need to then subtract 21 from both sides to move it to the other. So we end up with a negative 36 on the left and a 9x on the right. So once again I have another subtraction POE, property of equality. Line 6, we'll take that x and divide away the 9. We'll divide both sides by 9. So the final answer is negative 4. And this is our division property of equality. So there's two examples back to back where we are using algebra as a way to set up a two-column proof. And notice most of our operations are properties of equalities, except for the distributive property, which is not a property of equality, and except for the combined like term. So keep an eye on those two. Now in example 3 we're doing yet more algebra. It's really kind of the same thing, but with a twist. In the first two examples we've always been solving for x and getting a specific number. But now let's take a look at an equation that has just more variables. I want you to see that we can still isolate a variable even though you have lots of other variables inside that equation. So example 3 says the formula for the area of a triangle is area equals 1/2 base times height. Solve the formula for the base and write a reason for each step. So that'll be part 1. That's what we'll do first, and then we'll come back and then we'll do this specific calculation here where it says then find the base of a triangle whose area is 1768 square inches and whose height is 68 inches. Alright, let's kind of shelve that second statement for a bit. Let's focus on the first part. The formula for the area of a triangle is area equals 1/2 base times height. Solve the formula for the base and write a reason for each step. So that means set up a two-column proof. Here's my column for statements. Here's my column for reasons. Again, statement number 1 is the formula they give us. Area equals 1/2 base times height. And reason 1 is given. Now the goal here, they said, is to solve the formula for b, the base. So that's the variable I have to get by itself. That means we have to get rid of the 1/2. We have to get rid of the height. So that'll be 2 steps we're going to work with. Let's start with the fraction. If this is 1 divided by 2, then to undo that, I need to multiply both sides by 2. That way, 2 times 1/2 will cancel out. And this will give us 2 times the area equals base times height. Alright, so what was the operation I did? I multiplied both sides. So this is my multiplication property of equality, POE. Again, the goal is to get the base by itself. It is currently being multiplied by the height. So we want to undo that multiplication with division, and we're dividing both sides by h. That way the h's cancel out on the right-hand side. Now you'll notice that the h does not cancel out on the left-hand side, and that's okay. We are restructuring this equation with the goal of getting the base by itself, and now it is. So it's the same formula for the area of a triangle, but it's reformatted. Instead of the area being by itself, now the base is by itself. What this means is I have another formula where if I know the area and I know the height, I can plug them in and we can calculate the base directly. As far as finishing up the proof, I divided both sides by 8, so this is my division POE. So that's part 1, where we wrote a reason for each step. Now this is part 2. Then find the base. We can do that because we've got the formula now. Find the base of a triangle whose area is 1768. We'll plug that in for A. And whose height is 68 inches. We'll plug that in for H. Alright, so I'll just create a little separation here between these two parts. Alright, so here's my formula. My formula is 2 times the area divided by H equals the base. So let's plug in the numbers they give us. So 2 times the area is the 1768, divided by H, the height is 68 inches. So we have 2 times the 1768 divided by the height of 68. Notice my variable is already by itself, so I don't have to do any more operations. We just go straight to the calculator to type that in, and we get an answer of 52, and that's inches for the units. Alright, we have a few other properties to take a look at, so if you'll turn the page, let's finish up with some of these. We have more properties of equality. We have these reflexive and transitive properties that we want to take a look at. Alright, so at the top of the page, we have reflexive property of equality. This property can work with numbers, it can work with segments, and it can work with angles as well. So if we have a number, we're using this variable a just to represent that number. For any real number a, there is this property called the reflexive property of equality that says that number is equal to itself. Now that might seem kind of obvious. Of course a number is equal to itself, but there will be times when it's very handy to use this. We'll talk more about that in the future. It's also true for segment lengths, because remember, this is the symbol, it doesn't have the bar, it's the symbol for the length of a segment. So it's really just a number. We're saying that this number equals itself. It's just that this segment happens to be the number that we're talking about here. It's also true for an angle measure, because again, an angle measure is just a number. So the measure of angle A equals itself. That's the reflexive. That's how you spell it. R-E-F-L-E-X-I-V-E, reflexive. The transitive property always involves 3 ingredients. Again, it works for numbers, it works for segment lengths because they're also numbers, and it works for angle measures because again they are also numbers. So you have to have 3 ingredients. So here we are using the numbers A, B, and C. Those are my 3 ingredients. And we're going to link them together in this chain. If the first number equals the second number, and the second number equals the third number, then that means that the first is equal to the last. So this is sort of the chain of effect. If the first number is equal to the second number B, and the second number B is equal to the third number C, then the first and the last must be equal to each other. They're all equal to each other, in other words. If it works for numbers, it works for segment lengths, because they're also numbers. So if we have a segment length called AB, and a segment length of CD, and a segment length of EF, we can link them together in a chain. So if we know that the first segment length is equal to the second segment length, and the second segment length is equal to the third segment length, then what do we know about the first and the third? How do they compare? The first length is equal to the last length. And that concept also applies with angle measures. So we have angles A, B, and C. So if the measure of angle A equals the measure of angle B, and the measure of angle B equals the measure of angle C, then what do we know about how the first angle and the last angle compare to each other? We know that the first angle must equal the last angle. Think of it as links of a chain. The first link is connected to the second link. That second link is connected to the third link. So that means the first and third are not connected directly, but they're all on the same chain. Alright, so here are a few examples. You'll have some book problems like this, where they will say, here's the transitive property. See if you can fill in what would come up next. Alright, so the transitive property of equality, that's what we were just talking about here. Remember, there's always three ingredients. So, do you see them? R is one of them. S is a second. Oh, there's S again, so we don't count that twice. And there's the 44. So those are your three ingredients. So we're saying that if R is equal to S, and S is equal to 44, then how do we know how the first and third compare? We know that R is equal to 44. That's your transitive property of equality. Your reflexive property of equality. Reflexive, remember, reflexive means something is equal to itself. And so here we're talking about an angle measure. So the measure of angle N equals the measure of angle N. Here, this is taking us to the previous page when we're talking about the addition property of equality. So this is the statement. This is the equation we're starting with. Remember, you can add the same thing to both sides. And we're saying, hey, this is what we're adding to both sides. We're adding the length of xy on the left-hand side. We're adding the length of xy on the right-hand side as well. That's why it's the addition property of equality. So what goes in the blanks is the original equation. So that was my equation, RS equals TV, but we've added the same length to both sides. Lastly, the substitution property of equality. If the measure of angle 1 equals 20 degrees, then the measure of angle 1 plus the measure of angle 2 equals. Now it's not asking us to add up numbers to get an answer here. We're doing a substitution. What that means is we're going to take the measure of angle 1 out, and we're going to put 20 degrees in its place right here. So that's going to disappear, and we're going to have 20 degrees in its place. So that's the result of the substitution. We simply plugged in 20 degrees because that's how big the measure of angle 1 is.